A new kind of machine. Imagine a computer so powerful that it could solve problems in minutes that would take today's fastest supercomputers thousands of years. Sounds like science fiction, right? Yet this is the promise of quantum computing. In laboratories around the world, researchers are building machines that do not follow the ordinary rules of classical physics. Instead, they rely on the strange and fascinating principles of quantum mechanics. But what exactly is quantum computing, and why is it such a big deal? Let's begin our journey into this new frontier of technology. The limits of classical computers. Bits and binary. To understand quantum computing, we first need to understand classical computing. Every device you use today, from your smartphone to massive data centers, runs on bits. A bit is the smallest unit of information, and it can exist in one of two states, 0 or 1. Everything, videos, games, emails, artificial intelligence models, is ultimately translated into long strings of zeros and ones. The speed barrier. Classical computers have become incredibly fast, but they still process information in a fundamentally sequential way. Even with billions of transistors working together, certain complex problems, like simulating molecules accurately or factoring extremely large numbers, remain practically impossible. As our world demands more computing power, we are beginning to approach physical and practical limits. So what happens when traditional scaling no longer works? Enter the quantum world. Qubits, more than 0 and 1. Quantum computers use qubits instead of bits. A qubit, short for quantum bit, can exist as 0, 1, or both at the same time. This property is called superposition. Think of it like a spinning coin. While it spins, it is not just heads or tails. It has the potential to be both. Only when you look at it does it settle into one outcome. In a similar way, a qubit can represent multiple possibilities simultaneously. Entanglement, a mysterious connection. Another powerful feature of quantum systems is entanglement. When qubits become entangled, the state of one instantly influences the state of another, no matter how far apart they are. This isn't science fiction. It has been experimentally verified. Entanglement allows quantum computers to link information in ways classical computers simply cannot. Together, superposition and entanglement create an entirely new computational landscape. How quantum computing solves problems. Parallel possibilities. Because qubits can exist in multiple states at once, a quantum computer can explore many possible solutions simultaneously. Imagine trying to find the correct path through a massive maze. A classical computer would check each path one by one. A quantum computer, in theory, could evaluate many paths at the same time. This ability gives quantum machines an exponential advantage for specific types of problems. Famous algorithms. In 1994, mathematician Peter Shor developed an algorithm showing that a quantum computer could factor large numbers far more efficiently than classical systems. This discovery sent shockwaves through the world of cryptography. Later, Grover's algorithm demonstrated faster search capabilities. These breakthroughs revealed that quantum computing was not just a theoretical curiosity, it had practical, transformative implications. Real-world applications. Drug discovery and material science. One of the most exciting applications lies in simulating molecules. Nature itself operates according to quantum mechanics, which makes it extremely difficult for classical computers to model complex chemical reactions. Quantum computers, however, speak the same language as atoms. This could accelerate the discovery of new medicines, batteries, and sustainable materials. Optimization and artificial intelligence. Quantum computing also holds promise for optimization problems, such as improving traffic flow, supply chains, and financial modeling. While we are still in early stages, researchers are exploring how quantum systems might enhance machine learning. Could future AI systems think more efficiently with quantum assistance? The possibility is both thrilling and humbling. The challenges ahead. Fragile qubits. Despite the excitement, quantum computing faces enormous challenges. Qubits are incredibly fragile. The slightest disturbance, heat, vibration, or electromagnetic noise can cause errors. This phenomenon, known as decoherence, limits how long qubits can maintain their quantum state. Error correction and scalability. Building a large-scale, reliable quantum computer requires sophisticated error correction and extreme cooling systems. Many current machines operate near absolute zero. Companies and research institutions are racing to increase qubit counts while maintaining stability. Progress is steady, but practical, fault-tolerant quantum computers are still years away. The quantum future. So where does this leave us? Quantum computing is not here to replace your laptop or phone. Instead, it's a specialized tool designed to tackle problems that classical computers struggle with. Governments, universities, and companies worldwide are investing billions into research, recognizing its transformative potential. We stand at a moment similar to the early days of classical computing, when room-sized machines seemed impractical and mysterious. Few could imagine that those early experiments would eventually lead to the digital world we now take for granted. Could quantum computers follow a similar path? History suggests that breakthroughs often begin quietly before reshaping entire industries. Conclusion: a shift in perspective. Quantum computing challenges not only our technology, but our intuition. It asks us to accept that particles can exist in multiple states at once, and that distant objects can be deeply connected. It transforms computation from a straightforward sequence of steps into a dance of probabilities. As we continue exploring this frontier, one thing is clear: quantum computing represents more than faster machines. It represents a new way of thinking about information itself. The journey is just beginning, and the questions we ask today will shape the innovations of tomorrow. Are we ready to embrace a future where the rules are no longer strictly binary? Only time and quantum discovery will tell. Yet even now, prototypes are demonstrating steady improvements, inspiring a new generation of scientists and engineers to rethink what computation can be. Universities are launching programs, startups are emerging, and collaborations are expanding across borders, all driven by curiosity and ambition. The momentum feels both urgent and hopeful.